This lecture is about network input-output models. Here's the table of contents of what we'll be talking about today. We'll be talking about blocking, we'll be talking about multiplexing, we'll talk about non-blocking, and then we'll finish with multi-threading. Now, there are a number of different input-output methods that you can use for networking. And in this particular lecture, we're going to be talking about blocking, non-blocking, multiplexing, and multi-threading. There's also, in additional to that, asynchronous input-output as well, but we're not going to talk about that in this lecture or in this class. Now, keep in mind that this is a toolbox to choose from, and you can use a mixture of methods. For example, you could use a blocking with multiplexing, multi-threading. You could use non-blocking with multiplexing, multi-threading, etc. You don't need to use one or the other. You could use a group of ones if you wanted to. It just depends on what your application needs are and how best served with the different input-output methods. You would decide which one to use or which ones to use. So let's go through a simple question. What happens when cin is executed? And this is probably the first function that you used when you started learning programming. In programming 1 or 2 or whenever you learned that. Well, what happens when that's executed? If you write a console program, does it immediately return if the user does not input anything? Well, no, it waits for the user to input something before it is returned. So in this sense, we could say that the input operation in general has two distinct phases. The first phase is waiting for the data to be ready, and then after which, once the data is ready, for example, in the cin example, the user has pressed a key on the keyboard, then the second phase is copying the data from the kernel to the process, to your particular application. Okay, and you could analogously say the input output operation relating to network is the same, except now you're waiting for the data to arrive on the network. So you're waiting for that data to arrive from the network interface card into your machine, and then at which point the second phase can happen. You're copying the data from the kernel buffer to your application buffer. Now we talked about cin and its blocking. So other blocking functions that you used in this particular class in specific is accept, connect function, receive function, send function. Those are all blocking type functions, and the blocking functions wait until the requested operation completes or when an error occurs. And keep in mind, the blocking mode is default. So that socket that you create, unless you specify it is a non-blocking socket by turning some flags off and on, it is blocking. So any functions that it's going to call that blocking type function like accept, if there's no one waiting to connect to that server, then it will block until at which point a client tries to connect to the server, and then it will return. Okay, so just make sure that you are aware of that. So we said that accept is blocking. The connect is also blocking on stream sockets. The receive is blocking, and send is a blocking type function. Now this is a picture of an example of when a blocking function is doing the blocking thing. So you have your application on the left, your kernel on your right. Now notice this is one machine. This is not two different separate hosts. It's one host. You have your application and then you have your kernel. So your application, what it does, so it does a receive from call, a function call, and it's a system call to the kernel saying, hey, I want some sort of data if there's any sort of data from this particular port and IP address. So it does the system call to the kernel. But notice at the top right here that there's no data here at the kernel waiting for this particular application doing the receive from call. So no data has arrived from the network, from the network interface card, and so there's nothing to do. Now this function call is going to be blocking. It's basically just wait. It's going to wait for the data to get arrive. So at t plus some time later, data arrives, and at which point the second phase can go through now. So now the data can be copied from the kernel to the application. And once the the data complete is copied, the receive from returns. So receive from the time you call, receive from where there's no data to the time when data arrives to the time when the data is copied is completed, that whole time is blocking. So the process is blocked the entire time from when receive from is called until it returns. Now let's go over why this is an issue if you are a server, why this can cause problems. So in this picture here, you have a server on the left and clients A, B, and C on the right. Okay, so on the server side, there are pause this video and think about how many sockets exist on the server side right now. You have a so keep in mind that the clients A and B and C are connected clients. Okay, so the server on the side has 4 sockets right now. So the listen socket up here, and what this one is doing is listening for any incoming connections, any connection requests. There is the socket that's logically connected to client A, the socket that's logically connected to client B, and then the socket that's logically connected to client C. So there are 4 sockets right now. Now let's consider that this server is just in default mode, and all the functions that will block, if it's going to block, it will block. So let's go through an example. Now, if let's say that B has client B and client C has sent something and is waiting on the kernel side, waiting for the application to be picked up. Client A has not sent anything. And then client D is trying to get a connection to the server. So let's see what happens. Okay, so let's start the parse area. So the server does what it needs to do, finish up what it needs to do. Now the next step in the loop is go to listen. So it calls accept to see, hey, is there any clients wanting to connect to me? And oh, luckily client D is trying to connect. So in this case, the accept will not block because in this case, client D is trying to connect. So there's some data from the network waiting to be processed by this particular server. Okay, that's fine. So once that returns, okay, great. So the next function that this server is gonna call is to do a receive. So it's gonna try to receive something from client A. Now remember, in our example, client A has not sent anything. Client B and client C has, but client A has not sent anything. So at this point, when the server calls receive from the socket that's logically connected to client A, it's not ready. There's no data to be processed. So it's just going to wait. It's going to wait until at some t plus some time later when client A sends something, then it's going to process that data, copy it, and then return, and then it could go on to the next step in the loop. So notice how at this point, because there's no data from client A, it's just stuck at client A. So client B cannot be processed and client C cannot be processed either. You can see how this can be problematic due to the fact that a server is not typically serving only one client. A server typically serves more than one client. So why would you use blocking, just straight out of the box blocking I/O? Well, applications using blocking sockets are typically simpler to write. So if you have a server that only needs to connect to one particular client, then you don't need anything fancy, right? So you know that you're just going to have serving one client at a time, then it's not a big deal. You only are able to handle one pending task. You must wait for network operation to finish, and programs can appear to hang until some sort of timeout. So now, what if your server is someone that serves many different clients? What if you need to do other work in addition to just one particular client? Well, there are other things you can do, and one of which is called multiplexing. So here are some example times to use multiplexing. When a client is handling multiple descriptors, when a TCP server is handling a listening socket and connected sockets. Now, doesn't that sound like this particular situation here? You have your listen socket and then you have your connected sockets to clients A, B, and C. Well, perhaps multiplexing is something that you would want to do. Or a server handling TCP and UDP, or a server handling multiple servers and multiple protocols. So in effect, if you want to use your server to handle multiple things, to do multiple tasks, then perhaps only using blocking is not a good idea. So this multiplexing IO, you remember earlier I said that you can use it in conjunction with the blocking default mode. So I'm not necessarily saying that the socket type is non-blocking. It's still blocking type, but now we're using something called multiplexing method on top of it. Okay. So in this picture here, you have your application on the left and your kernel on your right. Again, this is the same host, same machine. It's not two different hosts. It's just the kernel side and then the application side. Now, instead of calling receive from directly, the first thing that the application does, what it does is it calls another function. It calls select function. So it does a select function, and it's also system call to the kernel. And the kernel gets that request and sees, okay, so I'm going to check to see if there's data on this particular socket that the application is calling select upon. And the kernel checks and there's no data. Well, after t plus some time later, data arrives. So at which point select returns. So now this data it's not copied. This data that just arrived from the network is not copied. What select is doing is alerting the application that, hey, yes, there is data that is ready to be copied. So now if you do receive from, it will not block. The information is there, so you can do a receive from without blocking. And you can see that on this picture here. Once that select returns, the application calls receive from to get the data that was arrived when the select returned that alerted the application. So when the application called receive from this point, it goes over here, the data is there, immediately it is copied, it copies the data, and once that data is copied, it goes back, this receive from returns. So here is a picture of what once we add the select function in there, in addition to the default mode of the blocking sockets. So let's see what happens in this case. So let's in the same thing. What we're gonna do is again the same situation. There's going for the listening socket. There's going to be client D that has called connect and is trying to connect to the server side. Client A still has not sent anything. Client B and client C has sent something. So something is waiting on the kernel side to be received. Okay, so let's go over through the parse. So after the parse, what the server does is calls select upon this group of sockets. So remember we said that there are 4 sockets here on the server side. One that's listening for any new connections, one that's logically connected to client A, one that's logically connected to client B, and one that is logically connected to client C. So the server calls select on this group of sockets and says, hey, which one of you is ready for this server to process? Well, select is going to return back and alert the server that listen is ready to be read, A is ready to be read, or so sorry, A is not ready to be read because we said that nothing, A has not said anything. B is ready to be read, and C is ready to be read. So at this point, the server knows that if it calls accept on this listen socket, it's going to not block because there's going to be some data waiting for that accept to be processed. And if it calls receive on the socket that is connected to client B, that is not going to block because there's some information there ready to be received. And the same thing for client C. And it also knows that client A is not ready. There's nothing there. So if it calls receive on that socket that's connected to client A, it's going to block. So what it's not going to call, it's actually not going to call receive on that socket because it knows that there's no information there to be processed. So what select does is selectively processes sockets. A select function on a group of sockets. Basically, you see which ones are ready and you ignore the ones that are not ready. So you're going to use a structure fd underscore set. And what that does is it represents a set of sockets. So you're going to put your sockets in this group, in this array, and then you're going to check to see if which ones are ready. And then once you see when it select returns, it'll tell you which ones are ready. And then so you could just selectively process those particular ready ones and ignore the ones that are not ready. So here are some of the conditions that you can check the readiness for. You can check to see if any of the descriptors in the set are ready for reading, basically meaning that if there is any information that has come in from the network and that is ready to be read into the application. You could also check to see if any of the descriptors in the set are ready for writing. So basically, you are checking to see if there's any buffer space in the kernel side to write out data so you can send it out. Basically, you're checking to see if your mailbox have enough room to put your mail in. You could also check to see if any of the descriptors in the set have an exception condition. And then you could also check to see if 10.2 seconds have elapsed. Now, 10.2 seconds is not exact. It's just an example. So you could check to see if any metric of time has passed. This is the select function, and you can see the parameters that it takes. So the first parameter just exists for compatibility reasons. The second one is you are checking for readability. So if you are using it, it's an optional pointer to a set of sockets. If you're using it, you are checking to see if this group of sockets, if any of the sockets in there is ready for reading, if any of information has come from the network. The third parameter is the optional pointer to a set of sockets that have to be checked for writability. So basically, you're checking to see if there's any kernel buffer space for you to write your data out. Basically, your mail in your mailbox, or if it's full. The fourth one is an optional pointer to a set of sockets to be checked for errors, and you could go on MSDN to see what particular exceptions that you could check for. You won't need to use any of that in the labs for this class, but you can go ahead and see if you wanted to. And the last parameter is a structure holding the length of time to block for at most. So you can, the last one is you could set a timeout if you wanted to, or you can just not block, or if you wanted to. We'll go over more on that in the next slide. And then you have the structure FD underscore set. So that basically represents a set of sockets. So you're going to make a FD underscore set that you'll place all your sockets in, and then you'll call select on that group of sockets. And you can use the set macros to manipulate. So you can use the macros FD underscore 0 to initialize your FD set. So if you create an FD set master set, you can initialize that set to empty set. And then you could do FD underscore set to add socket to your particular set. So if you have an FD set read set, you could put your socket, your listen socket into that set using FD underscore set. And every time you connect you have that logical connection to the new client that is formed, and the new socket returns, you place that new socket into your FD set using FD underscore set. So you can also use FD underscore clear as well. So it removes a socket from the set. So if you have a server that serves a certain clients, and the client says, hey, I am done with this connection and I want to terminate this connection, well, you can remove that. After you have terminated the logical connection to that particular client, you can remove that set from the FD set. And then finally, the last set macro that I could do is FD underscore is set. And that is true if S is in the set and false otherwise. So you would use FD underscore is set to check. So once you have selected on a group of sockets, you can use FD underscore is set to check to see if that socket is in the set. And if it's true, that basically what it means is that the data is ready to be processed. Because note, look at the note. This is very, very important. Select modifies the sets that are passed in to reflect ready sets. So depending on the option specified. So let's say that you use the select function and you do the optional pointer to a set of sockets be checked for readability. So the second parameter. So you're using that second parameter. Well, you are checking to see if your group of sockets have any data ready. So going back to our example here, right here, we have clients A, B, C, and listen socket, and let's just say that client A does not have any information. So client B has information, client C has sent information, and there is a client D trying to call connect. Well, when you call select on that, what will happen is originally that FD set that you initially created will have four sockets in it, right? That original FT set would have four sockets: the listen socket, the socket that's connected to client A, the socket that's connected to client B, and then the socket that's connected to client C. So when you call select on the FT set, it modifies it so that it only will reflect ready sockets. So in our particular example, when select is called on that set becomes the listen socket, the socket that's connected to client B, and then the socket that's connected to client C. So the socket that's connected to client A is not going to be in that set. It's not going to register. It might be under uh, if you look at the structure, if you do debugging, and if you walk through it, and if you look at that FD set, it will still have the integer value that's connected to that data structure on the kernel level, but it's going to dynamically resize that array so that it will only reflect that that array has three sockets instead of four sockets. Okay, so this is what select does. It modifies the sets that are passed in to reflect ready sockets. So that last parameter that you can use is also a timeout structure. So you can do the struct time eval, and you can specify the seconds and microseconds. So it defines a specific length of time in seconds and microseconds, and it's used by select to determine blocking time. Now those two parameters, they're additive, so they will just add together. So the microseconds just give you a little more granularity in how much you want to wait for. Now, for select function, there are three interpretations of the timeout. So you could do no for that particular parameter. And what that means is that you just basically want it to just wait until at least one of the sockets in this FD set is ready to be processed. So just block until some data has arrived from the network. The second parameter, the second interpretation is if you do a fixed time, so if you do like 10.2 seconds, like in the example I did in 2 slides previous, what that says is you want to wait for that specific amount of time, or if the information has arrived before that time has elapsed, go ahead and return also. So either you want to wait for that time, and if no data has arrived, you just want to return, even though no data has arrived. Or if data has arrived before that time has elapsed, then go ahead and return before that time. Now, the third interpretation of the timeout is you could put a 0 as the parameter. What 0 does is just don't wait, just don't block, just go ahead and check. And if there's nothing there, then just come back. Even if there's nothing there, just come back. It doesn't matter whatever the condition it is, just come out, just check, and then just come back. So just note that regardless of the timeout value, select will return as soon as any socket enlisted is ready. So the socket in your group of sockets is ready. So I'm going to go into readability a little more. I just want to emphasize it a little more, just because you will need to check for that in your lab 3, where you're working on the server side of PokeChat. What does readability mean? Readability means that the queue data is available for reading, such that a call to receive or accept is guaranteed not to block. So for your particular lab 3, server side of PokeChat, remember you're not only checking to see if a socket is ready, if a client has sent a message in PokeChat. You're also checking to see if any additional clients are waiting and trying to connect to the server. Okay. So this is the setup in general for select. You acquire a listen socket and client sockets, like you have been doing. So your example is lab one, where you had the spaghetti relay server side, where you had listen socket, you defined it, you gave it value, and then once you called accept, then you have that client socket that's connected to that particular client that finished that connect call. So same thing. So you acquire listen socket and client sockets, and then you create a master set of sockets. So a master set of FD set. You zero out the master set using the macros listed in the earlier slides, and then for each socket that you have, you want to add it to that master set. So you want to add your listen socket into the master set. You want to add any of the already connected clients or if you connected clients, you want to add that to the master set. So during the run the server side, if a client calls connect and it finishes the three-way handshake and you want to accept that client into your server, then you want to add that socket to the master set. Additionally, you could also set out a timeout value. You don't have to, but you can if you want to. Now, so that was set up. That was the to set it up. Now, how would you use it? So notice the first line. You are you are creating a read set from the master set. Remember, we talked about this earlier. When you call select on a set of sockets, what it does is it modifies it. So it modifies to reflect the ready sockets, and it resizes that array so that only the ready sockets are counted. The non-ready sockets are not counted at all. So it modifies your master set. So that's why you need a reset. You do not ever want to call select on your master set because you want to keep track of all the sockets that are currently active. Like in our particular example of the server that's connected to client ABC, even though A has not sent anything in this round of looking, it might want to send something in the next round. So you still want to keep track of that socket, even though it doesn't count on this round. So just keep in mind that you need a ready set and a master set. You do not want to call select on your master set. Okay, so the second line is you call select, and now notice that it has two parameters that it specifies. It has specified to see if any of the sockets are readable, and it also gave a timeout value. Okay, and then the next line is once the select has returned, it's going to check is the listen socket now in the reset? Is the listen socket in the reset once it's been called select upon it? Well, yeah. So if it has, which it has in our particular example, remember client D was trying to connect, well then it accepts a new connection. Now notice that because it accepted a new connection, that logical connection to client D. Remember, don't forget to put that in the master set so that in the next round of polling, you should be able to see if anything is ready from client D. Okay. So once that listen socket is checked, and then you would go ahead to check to see if any of the existing logical connections in the reset is ready for processing. So in this case, client A would not be in the reset, but client B and client C would be, and so they would process them and do a receive on those. So here's some pseudocode for multiplexing server algorithm. You can go ahead and read it when you get a chance.